Okay, I want you to try to solve these three differential equations. It shouldn't take long. These problems are pretty short to do. Okay, now let me know if you are not able to record and you want to. Let's see, I think I got everybody.
Oh, could I get permission, please?
What is your name? Okay,
Harvey?
all right, I think I got it. Yep. Okay, you should have permission now.
Thank you.
Okay, so based on what we learned yesterday, um, we want to solve these three problems.
Professor,
Yes.
I have a question. So the exam, it will be like this Thursday, right? The second
Well,
exam.
I'm not sure yet. It'll either be this Thursday or next Tuesday. It depends upon, if I'm able to cover everything that we need to cover.
Oh, okay.
Okay, so it may not be this Thursday. Okay.
Oh, okay.
It's the first time I'm teaching this course in 6 weeks, so I wasn't really sure how to break things up. Like I got a full week for Power Series, and I don't think we're going to need a full week for Power Series, but we may need a little bit more time for this. For the topics we're doing now. Okay, so everybody should be working these three problems. The last one is not factorable. Okay, when you find the auxiliary equation, you won't be able to factor the last one, but the other two you could factor. But it should be a prime here. I like to make sure that you at least get a chance to try the last one. Okay, I'm going to give you one more minute. It shouldn't take long, but I just want to, I hope that everyone gets a chance to try the last one. All right, I'm going to go ahead and solve these three equations. So remember yesterday, we started out where we assumed the solution of this form, right? But you don't even have to do that, right? When I have this differential equations, all you need to do is you can immediately write down what we call the auxiliary equation, right? So the auxiliary equation for this is m squared plus 15m plus 56 is equal to 0, right? That's the auxiliary equation for this differential equation. Then I can factor this, right? Let's see. We could factor this into m plus, I wanted that to be a minus sign. No, it's okay. All right, so we want to factor this into m plus 7, right? And m plus 6 is equal, m plus 8, sorry. I was thinking 56. All right, so this is factorable into m plus 7 and m plus 8. And so m is equal to minus 7 and m can be equal to minus 8. So the solution to this differential equation is equal to C1 e to the minus 7x plus C2 e to the minus 8x. All right. So that's the solution to this differential equation. So you can immediately just write down the auxiliary equation and then solve for the roots of m. Now this one here, all right, the auxiliary equation is m squared minus 14m plus 7, 49. I'm doing the factoring in my head already. So this is 49 is equal to 0. All right. So so I can factor this into m minus 7, right? And m minus 7, right? So that gives me the middle term of 14, right? And then minus 7 times minus 7 gives me the 49. So now this is m is equal to 7 and m is equal to 7. So now in this case here, we have repeated roots, right? We got repeated roots. And remember, we showed that when we have repeated roots, well, we need another linear independent solution, right? So one solution is y is equal to C1 e to the 7t. And then we showed yesterday too that if I multiply this by x, I can get a second linear independent solution. All right. So make sure that if you got repeated roots, it's real simple, right? Repeated roots, you have C1 e to the 7x, and then to get the second solution, you're just going to multiply by x. All right. So don't forget to multiply by x to get the second solution. Okay. Any questions? So this is kind of like what we did yesterday. All right. Now, in this problem here, remember the quadratic formula, let's say m is going to be minus b over 2. Oh, well, let me put a, and in this case it will be 2. Let me put a 2a. All right, plus or minus. I'm going to write it like this: the square root of b squared minus 4ac. Right? Everybody can see what I'm writing. Oh, not going off the page. Divided by 2a. All right, so that's our quadratic formula. So let's see. So this is, I got minus 6 divided by 2, right? A is equal to 1, minus 6 divided by 2, plus or minus the square root, and this is going to be 36 minus, it's gonna be 36 and minus 80, right? I wanted this to be 25. I wanted this to be 25. Okay, you might have did it for yeah, I wanted this to be 25. So then this becomes 100, right? Divided by 2. So if it didn't come out the way I wanted it to come out, guess I copied it wrong. All right. So anyway, so this is 25. I made up these problems. So this is 25, right? So then 4 times 25, yeah, 4 times 1 times 25, that's 100. Okay. So then this is now m is equal to minus 3, right? Plus or minus the square root, and then this is minus 64, right? 100, well, 100 minus 36 minus 100, that's going to be minus 64 divided by 2. So this is m is going to be equal to minus 3 plus or minus, now this is going to be 8i, right? This is going to be 8i. I'll do all the steps. This is 8i divided by 2. So I can write this as m is equal to minus 3 plus or minus 4i, right? I did that right? Okay. I guess if you put the 20 in here, it was a little bit more messier. You know, you're gonna get 80 here, and then you get 36. So you're not gonna get a perfect square. But anyway, I wanted to illustrate this because it turns out that the solution, when I get an imaginary, okay, the solution to this differential equation is going to be y is going to be equal to c1 e to the minus 3x, right? Here I got the 3, and I'm going to show you this is true. C1 e to the minus 3x, and then here I got a 4i, right? Well, it turns out this 4i is going to be cosine of 4x, and then the second solution is going to be c1 e to the minus 3x sine of 4x, all right? So in other words, and I'm going to show you why this works out, but in other words, the what you're going to do is if you end up getting complex conjugates, right? Complex conjugates, like here I got complex conjugates. This is going to turn out to be sines and cosines. All right. So yeah. So whenever if you see a 4i, you're going to make that a cosine, and you're going to make it a sine. All right. For example, if this turned out to be I don't know, it turned out to be 3i, right? Then you're just going to put a 3 in here. Okay. It's actually as simple as that. So let me just do, before I go on, this is in my notes somewhere, I'm sure it is. But let's say you had this differential equation here. Just let me do, let's say
Sir, can I have permission to record?
okay, what is your name?
Connor.
Who's that? Connor. Okay, got it. I did have it. You know, your name. Someone else just came on. Okay. Okay. All right. All right. So now got y double prime plus 60. Let me make it 64. Y is equal to 0. Okay. Well, what is the solution to this differential equation? Well, what is this? This is actually m squared plus 64, right, is equal to 0. In other words, if I write the characteristic equation, all right. Now, this equation here, right, this is the same as m squared, right, is equal to minus 64, right? M squared is minus 64. If I take the square root of both sides, I get m is equal to, well, let's see, this is going to end up being plus or minus, right, 8i, right? When I take the square root. So, so what does that mean? Well, for this particular case here, for this differential equation here, the solution to this differential equation is equal to y is equal to C1 sine of 8x plus C2 cosine of 8x. All right. So the imaginary, when you find the characteristics, when you find the solutions to the auxiliary equation, whenever you get an imaginary part, that's going to be equal to sines and cosines. And you could take the derivative of this and see that you'll get this back. It's pretty easy to do. Okay, so I guess what I want to do now is actually give you a little bit of an indication why this works. Let's see.
Excuse me, Professor.
Yes.
Would you mind going back to the previous page?
This one here?
Yes.
Okay.
So, if you're left with a number outside with the minus b over 2a, then you would still have to put the e in, right?
Correct. This is real, right?
Oh,
So-
that's real. The imaginary is the 4x part.
Exactly right. So this is a -3. So the -3 goes with the exponential, right?
Okay.
And the 4x, the 4i here goes with the sines and the cosines. The plus or minus 4i goes with the sines and the cosine.
Okay. And I believe you just went over an example where, if you go back, where it's the same number, right? Oh, yes, it is.
Right, here we get plus or minus 8i. We don't see, in this case here, there is no exponential, right?
Right.
So when you solve this, this is the auxiliary equation, right? And you can use the quadratic formula, but there's no b. B is equal to 0, right?
Right.
You would use the quadratic equation, b is equal to 0.
So it's immediately complex.
Right, it's only complex there. You just get the complex conjugate. So you end up
Okay.
getting sines and cosines.
That makes sense.
Yeah. Please, if you have questions,
Professor,
Professor,
yes,
question. So
Sure.
doesn't matter where you put your sine of 8x or cosine of 8x, for example, can I put for your answer here C1 cosine of 8x and then C2 sine of
yes,
8x?
it doesn't matter. That's right. Okay, you could, this is exactly the same. If I put C1 cosine of 8x plus C2 sines, exactly the same. The thing is, the constants will, when you put in initial conditions, you'll end up getting the same equation, but it doesn't matter what you call them.
All right, and does that also apply for previous problems?
Yes. It
Professor-
doesn't matter in all the problems. It doesn't matter which one, these are called the fundamental solutions. Remember, that's one of the things we talked about, and that it doesn't matter which fundamental solution. If I have like a y1, a y2, and a y3, I can put any C1 or C2 in front of these. Okay, it doesn't matter. Okay, and other question? Was there another question?
yes, Professor. So for that, is it always the case that it's like either sine or cosine, but it's always a positive, or like there will be like some cases like it will be a negative?
No, it's always if this is complex. No, this is always going to be 8x, and it's always going to be, this is plus or minus, right? So
Yeah.
this is actually going to give you sine and cosine.
Yeah, but like my
Let me
question
go
is,
ahead. Go ahead.
yeah, it's my question is like, is it always like the case like?
Yeah,
It's like
this is always going to be a
C1,
positive number. This will always be a positive number.
yeah, so it's always be a plus sign in the middle of between them, like the cosine and sine.
Yeah, this is
Like-
always going to be plus or minus, right?
No. The question is like, so when we like rewrite it, yeah,
Oh, to be you mean you could actually it wouldn't be wrong to make that a minus sign, but you
Oh.
normally don't do that, okay? Because when you solve when you put in initial conditions, it'll come out where if you make this a minus C2 or a plus C2, when you apply initial conditions, you'll end up getting the same exact equation for y. but normally it's practice to make your constants plus.
Oh,
You-
okay.
You'll end up confusing, you can do it that way, but you'll end up, having to deal with more minus signs and stuff. Okay,
Okay.
did I answer your question?
Yeah.
Okay, all right.
Thank
Let's see, trying to. Okay, all right, so what I want to do now, see if I can find this. Okay, so, let's see. If I could use this. Okay, so, so remember now, so in general, if we have something like this, remember yesterday we talked about 3 different cases. One case where we have distinct real roots, and then the second case is where we had repeated roots, okay? And now we got roots that are complex conjugate, okay? So this is the case where, remember now, the quadratic formula, well, let me write this. The discriminant is given by this here, right? This is called the discriminant. It's 4AC. This is 4AC. Okay, now we're saying the 4AC is going to be less than 0, so it's going to be negative. 4AC is going to be less than 0, it's going to be negative. Now, this is my quadratic formula. Right, that's the quadratic formula. And what happens is that this here, right? This here, I'm going to call this alpha, right? This is alpha. And then this here, plus or minus, this is actually going to be complex, right? If this is less than 0, this is going to be complex. So I'm just going to call this I beta. If you follow what I'm doing now, that's fine. So that means that, just like what we had before, that y is equal to some constant k1. Now, I'm just using k for a reason. Hopefully you'll see. Some constant k1, e to the alpha, right, plus beta. I left out the I. Plus I beta x, right? That's one solution, right? Because remember, we said that when we solved the differential equation, we showed this yesterday that this is how you get the auxiliary equation. So the solution then would be alpha plus I beta x plus k2 e, and then it'll be alpha minus I beta times x. So these are my 2 solutions, right? In terms of complex or complex conjugate exponentials, all right? Now, I don't know how many people heard of Euler's equation, but Euler's equation tells us that e to the I theta, right? If you're taking some other is equal to, it's unfortunate that in calculus 1, 2, and 3, you don't see this. E to the I theta is equal to the cosine of theta plus I sine theta. How many people have seen this formula before? Has anybody seen this formula?
I've seen it.
Okay, good. All right. Let's see. Okay, so and then e to the I theta is equal to cosine of theta minus I sine theta, right? But I want to put a minus sign here. Okay, so so what I'm going to show you that using Euler's equation, I can get sines and cosines, right? But the important thing is really just to understand that that this beta here, whatever beta turns out to be, that's what you're going to put in the sine and cosine argument. And whatever alpha turns out to be, that's what you're going to put in the exponential argument. Okay. So let's see. So let me know if I go off the page. So I can write this as y is equal to, I'm going to write this as k1. I'm going to write this as e to the alpha x. And then I'm going to write this here, right? I'm going to write this as cosine of beta x plus I sine of beta x. That's supposed to be a beta, not a b, plus k2 e to the alpha x. And this is in my notes, cosine of beta x minus I sine of beta x. Okay, so as all as I did here is a bracket here. As all as I did here was that I took this I beta x, right, and I broke it down, right. In other words, let me put another step in here. I can write this like this, right? I can write this like this. So now I'm using this equation, replacing this with this. I'm using this equation, replacing this with this, right? And this is Euler's equation. Okay. All right. So now though, what I could do now is that I'm going to bring this constant through. Yeah, let me do it this way. That's the way I did it. Okay. So I'm gonna write this now as y1 is equal to k1 e to the alpha x. No, I don't want to do that. I want to, yeah, no, that's right. E to the alpha x. Cosine of beta x. And I'm bringing this through here. So now I'm going to write this as plus. Now here I got a k1 times I. So I'm going to call that k. Yeah, I'm going to call that k3. It's a new constant, right? It's a new constant. I'll call it k3. I already used k2. So this times I is k3. And then there's going to be e to the alpha x cosine of beta x. This is the way it's done in your book, by the way. And then here I'm going to write this as k2 e to the alpha x cosine of beta x. And I'm going to write this here as plus k4. I can call it plus or minus. Let me call it minus. So I think that's what I did in my notes. Call this minus k4. So in other words, k2 times I'm now calling k4. And then this is the sine of beta x. This is exactly the way it's done in your book. Okay, so now I'm just going to combine. Here I got a k1. In other words, these two equations here, the way I've written them, they're linear dependent. So in other words, I'm going to write this. I'm going to write this as y is equal to k1 plus k2 e to the alpha x cosine of beta x. And then I'm going to write plus, I'm going to write this as k3 minus k2 e. I forgot to make sure. Oh, I forgot the exponential here. Right? You write this as okay. This is now e to the alpha x, and then this is sine of beta x. Okay. All right. So now, I'm just going to write this as y. I'm going to call this k1 plus k2. I'm going to call that c e to the alpha x times cosine of beta x, and I'm going to call this c1. And then this here I'm going to call c2 e to the alpha x sine of beta x. Okay, so that's showing that using Euler's formula that these are imaginary exponents are actually sine and cosine. I don't know how many students are aware, but you know that sine of x is actually also e to the I x minus e to the minus I x divided by 2I. This is another way of writing sine, right? That's another way of writing sine. And cosine, another way of writing cosine is plus sign here, minus here. That's another way of writing cosine. Okay. And, you know, these actually come from Euler's formula. It's another form of Euler's formula. All right. So, so that being said, but the important thing that what I want you, let's see if I got something here that take a look at my notes here. Okay. All right. Why don't let's now you don't have to go through that formula. I want you to give you a minute now. Make sure you understand. Solve this problem, and then I'll do it. Let me give you a couple of minutes to solve this problem. Like this is going to end up being sines and cosines and exponentials. I'm going to give you another minute. All right, let me go ahead and solve this. So the first thing I'm going to do is I'm going to write down the auxiliary equation, right? I'm not going to go through all the, I kind of tried to show you why all this works. But so the first thing we do though is we write down the auxiliary equation, right? That's my auxiliary equation. And now I have to find the roots of m. I got to find the roots. And in this case here, this one's not going to be factorable, so I got to use a quadratic equation. Right, so this is my quadratic equation. And let's see. So I'm going to have a 5, right, over 2, right? You have a 5 over 2. Then I've got a plus or minus. I'm going to square root here. And then this is going to be 25, right, minus 4. And let's see, this is going to be it's 4AC. So it's going to be times 2 times 6, right, divided by 2. Right? So this is going to be 5 over 2 plus or minus.
Professor?
But it's 5 over 4. 5 over 4. Right, it's 5 over 4. I forgot the. It's 5 over 4. Was that your question? And this is over 4.
Yeah, that's what I was going to say.
Thank you. And this is over 4. Okay. All right. Okay. So let's see. So this becomes 25, and then this is minus 48. Yeah, this is 20. So this is minus 48 divided by 4. So this is yeah. So this is going to be 5 over 4 plus or minus the square root of 23, right? The square root of minus 23. Let me put in the minus 23 over 4. And then I can write this as 5 over 4 plus or minus I square root of 23. Square root of 23. Square root of 23 over 4. Okay. So so these are my roots for m, right? 5 over 4 plus or minus I times the square root of 23 over 4. Okay. So all right. So the solution to my differential equation is e to the 5 over 4 x, right? That's what I put in for the exponential. And then see, I can write this as C1. I'll show you the cosine. And then this is going to be the square root of 23 over 4 times x. I'm writing it times x. This is the argument. And then this would be C plus C2. Should I do it that way? I'm writing it where this is times both of them. I'll show you there's different ways of writing this. Okay, and then this would be a closed bracket here. So in other words, I'm making the exponential times this and this. Let me make this clearer. This is important. So I can write it like this. Right, so the exponentials times both. Or you can put the exponential in here, right? It's 2 different ways. I mean, I can also write it like this. Hope this is obvious, right? I can write it like this. I can write it as C1 e to the 5. I just want to make it clear that the exponential is actually times both the sine and the cosine. So you can factor it out and write it like this, or you can write it like this. Sometimes it's easier to write it like this when you have to apply initial conditions, because you're gonna have to use the product rule for the second derivative, all right? And taking the product rule of this is easier than taking the product rule of this and then the product rule of this. So anyway, I find it easier sometimes when you have to solve the initial value problem is to use this form as opposed to this. You just have to take the product rule of this. So anyway, but either way works. Any questions? So we should all be experts on solving second order homogeneous differential equations with constant coefficients. You know, in the WebAssign, there are some which have third order, but you know, I've worked in industry for 40 years and I never had to solve a third order differential equation. And it's not going to be much different. You just have to figure out how to find the 3 different roots. Okay, so let's just get a little bit of practice. And you do have problems. These problems in the WebAssign you need to get going on. They won't take long, but it turns out to solve the non-homogeneous differential equation. In other words, when we have a function here, those problems are longer. All right. So let's see. So I'm going to give you. Let's see, just to make sure everybody understands this, right? In the past, I found that these type of problems students get right. So. Let's see. So I'm going to try to solve these 3 problems without looking at my notes. And there's actually even some more. Well, I want to give you one more. This one is actually, maybe try this one first. Sometimes the easy ones are the trickiest. Actually, try this one first. I want to make sure you understand what's going on here. Oh, I'm sorry, I forgot something here. That's what I want. So this is y double prime plus 2xy prime. Okay, I'll give you another minute. These shouldn't take too long. Maybe another 2 minutes. All right, let me go ahead and solve these problems here. I want to solve this one first. So first of all, the auxiliary equation, right? This is going to be m squared plus 2m is equal to 0, right? That's my auxiliary equation. I can factor an m out, right? I can write this as m plus 2 equals 0. So this is telling me that m is equal to 0 and m is equal to minus 2. So what's e to the 0? Well, e to the 0 is just 1. So the solutions to this differential equation turns out to be C1, some constant C1, plus C2, e to the minus 2x. Okay? Sometimes this tricks students up that, okay, I got a 0 here, do I, but this is e to the 0, you just follow the rules that you learned in algebra, right? E to the 0 is just 1. So one of my solutions is just C1 times 1. All right. Any questions on this? I found that students get screwed up with that. Okay. So let me let's see. I don't have enough room to do this one here. Well, let me do this one down here. Okay. So immediately my auxiliary equation is right. That's my auxiliary equation. And oh, this is a 4. Oh, which one am I doing? I'm doing this one here. Oh, okay. All right. So let's see. So I could factor this. I could factor this into 2m. Let's see, 2m. It's going to be 2m minus 3. I need that 3m there, and plus m. Let's see, plus 3. This times this gives me the minus 3. This times this. Wait a second. Okay, this times this gives me the 6. And then this times this gives me the minus 3. Okay. All right, so I can factor this like this. So then this is m is equal to minus 3. And this here is that m is gonna be equal to 3/2. Plus, this is minus, right? That's plus. Okay. So, so the solutions is y. Doesn't matter which one. It's gonna be y c1 e to the 2/3 x plus c2 e to the minus 3x. I may have a different margin. Yeah. Okay. All right. Piece of cake, right? Piece of cake. All right. So now let's. So I just did this one. Let me do this one here. So now we got 4. Okay, so my auxiliary equation is this. All right, that's my auxiliary equation. And let's see, I can factor this into, let's see, this will be 2m plus 1 and 2m plus 1, right? This times this is this, right? So this, okay. Right? Okay, so so here I'm going to repeated roots, right? M is going to be minus 1/2, and here I get n is equal to minus 1/2, right? So the solution to this differential equation is y is going to be equal to e to the minus 1/2 x plus c1 plus c2. Now I'm going to put an x e to the minus 1/2 x. Okay. See. All right. And the last one, I'll do the last one. Okay, that was the last one. All right, so let's see. But let me write down. Okay, so this is not going to be factorable. Well, you can factor it in terms of imaginary numbers. Okay, but we're going to use the quadratic equation for this, right? So I'll write down the quadratic equation. And then this is going to be my m's, right? So let's see. So let's see. So this is going to be minus 4, right? Divided by 2a, so it's just 2, right? So actually my exponentials, let me put it down here. My exponentials, you can have a minus 2, right? The exponentials, you can have a minus 2. And then I'm gonna have plus or minus. Let's see, this is, okay, so it's gonna be 16 minus 4, and then times 10 divided by 2. All right. So let's see. So this is gonna be plus or minus. Okay, this is 40 minus 16. 40 minus 16 is 24. Is that right? Over 2. Right. And let's see.
Isn't it negative 24?
Oh, negative, right. Exactly right. Negative 24. Right. So then I could write this as minus 2 plus or minus. Let's see. I square root of 24 divided by 2. And I guess I could simplify this, right? Simplify this as, let's see, 6, 4, right? You don't have to actually, well, you should, you could leave it like this. I wouldn't have, if you left it like this on an exam, I wouldn't have a problem. But, you know, 24 can be factored into 6 times 4, right? So I can also write this as minus 2 plus or minus 2i times the square root of 6 divided by 2. Yeah. Right. So this is, yeah, maybe it's even better to do. So this is minus 2 plus or minus
Hey,
I,
Professor, if oh, is A just one?
excuse me,
Oh no, never mind.
right? I'm saying here that 24 is 6 times 4. And then the square root of 24, the square root of 4 is 2. So I'm writing it as 2I square root of 6, right? And this is divided by 2. No, I'm sorry, it's not divided by 2. I already divided by 2, right? This 2 cancels with this 2. So my final result is minus 2 plus or minus I square root of 6, right? That's my final result. So my solution to this differential equation is y is equal to e to the minus 2x, right? It's e to the minus, I got the 2 minus 2 here, so it's e to the minus 2x. And then here where I got the I square root of 6, I'm going to write that as C1 cosine of the square root of 6 times x plus C2 sine times the square root of 6 times x, right? And you can write it like this. So once again, I could write it with the exponentials times each one of these. Okay. So that's how we solve homogeneous, second order homogeneous differential equations with constant coefficients. It turns out that these differential equations have a lot of applications. These types of differential equations turn up a lot in electric circuits and also on spring mass systems, vibrational systems. And so we'll look at some applications. Okay. Any questions? Because what I want to do now, I want to start solving differential equations that look like this. I don't want to square this. Where we now have, where it's not non-homogeneous. Okay, I want to start looking at non-homogeneous. Now, it turns out the non-homogeneous problems could be a bit longer than the homogeneous. Okay, remember the homogeneous is when we set it equal to 0. The non-homogeneous when we have some function here where it's not equal to 0. All right. So before I go on, I want to start with the homogeneous, and we'll probably won't finish it today. But before I go on, I assume that everybody's good with this, right? It's pretty straightforward, because if you don't understand this, then you're not going to understand the non-homogeneous. Okay. All right. So let's see. All right. So now we're going to take a look at differential equations of form like this. Am I putting me double prime by the A's? I have a toothache, and I think that's causing my brain to function differently. Okay. All right, so now we want to solve differential equations of this form here. And so let me show you how this is going to work. I'm going to do it with an example. And this is one of the ones when we did preliminary differential. Remember when we had the lecture on preliminary differential equations? This is one of the ones I used as an example, so I want to continue to use it. Well, first of all, when we solve differential equations, remember we talked about this yesterday, that when we solve differential equations, we're going to find the solution. First, we're going to find the solution to the homogeneous differential equation, right? In other words, first we're going to find the solution to this. Right? And then we're going to find the solution. We're going to find the solution that gives us x squared on both sides of the equation. All right. And it turns out you have to do this first, right? And the reason why you have to do this first is because sometimes you may get a function that on this side of the equation is the same as, it's not linear independent with your solutions here. So then there's something that we have to do to make this linear independent. Now, so for now, just understand that you have to solve the, you'll see, maybe not today, but you'll see tomorrow. You have to solve the non-homogeneous differential equation first, okay? So anyway, so if I want to solve this equation, right, I want to solve this equation, the first thing I need to do is solve this. All right, I solved this. Now, the solution to this, and it may turn out that right, if I, hopefully everybody sees that the solution to this is just plus or minus 2y, right? I bring this over to here, and you get minus 4. You take the square root of both sides, and because it's negative, I get plus or minus 2y. So therefore, the solution, which we call the complementary solution is going to be equal to C1 cosine of 2x plus C2 sine of 2x. Okay. Now I want to find the particular solution. Okay. The way we find the particular solution is that I have this function here. This is x squared. I assume a solution that, by the way, this is called the method of undetermined coefficients. There's also a method called variation of parameters, which I wish we were doing. It's not required. It's not required for this particular. I actually wish we were doing variation of parameters. I will put variation parameters in my notes if any of the students are interested, but we're not gonna have it on the test because it's not a requirement. The curriculum doesn't require us to do it. So anyway, so this when we assume a particular solution, we assume the function plus its derivatives. In other words, here I got an x squared, okay? So I'm going to assume a particular solution that's of the form ax squared. Now the derivative of x squared is 2x, right? But it's just going to be, I don't have to worry about the 2 because I'm just going to multiply by constant. So I'm going to make this bx plus c, all right? So if I have a function on this side that's x squared, I'm going to assume a particular solution of this. Okay, so that's the first thing. Now, if suppose I had x, not x squared, then I would assume a particular solution of ax plus b, right? If this was x cubed, okay, I would assume a particular solution of ax cubed plus bx squared plus cx plus d, right? So basically you're assuming the derivatives of the function, all right? So that's the first thing to understand. But let's go ahead now. Let's go ahead now and let's see, this was the equation here. And remember the complementary solution, what was the complement? It was C1 sine of 2x plus C2 cosine of 2x, right? That's the complementary solution. All right, so now I'm going to assume a particular solution of ax squared plus bx plus c, all right? So I'm going to assume a solution of this. Now what I'm going to do is I'm going to determine what a, b, and c are, right? I'm going to put I'm going to take this derivative, I'm going to put it into, I'm going to substitute into this equation, and and I'm gonna match coefficients, and that's gonna tell me what A, B, and C are. So in other words, so first I gotta take the first derivative, right? So this is gonna be 2ax plus b, right? And then the second derivative, this is just gonna be 2a, right? Did that right? Okay. Then I'm gonna substitute it into this equation. All right. So in other words, now I'm going to do this. I'm going to put my y sub p's. Now in this case, I don't have a first derivative. Okay, I just have a second derivative in the function. So this is going to be 2a. Here I'm going to have 2a. Then I have plus 4, and then it's going to be times ax squared plus bx plus c, and this is all going to be equal to x squared, right? So far, so good. Okay, so now so this is going to be 2a plus 4ax squared plus 4bx plus c is equal to x squared.
Excuse me, Professor.
I left the 4 out. Yes, was that the question? I left the 4 out here.
Oh, no. My question is I noticed you said assuming y of d is equal to ax squared, that the first line. So is the assumed what's going to be given in the problem, or is
No. When you see an x squared,
right?
okay, you're supposed to know that this is what you have to assume.
Oh, okay, gotcha.
Okay. Yeah, you're supposed to take with the derivatives of this, but then you forget about any constants that are in front of it.
Right. Okay.
As we do, if once again, if this was x cubed, I have to assume ax cubed plus bx squared plus bx plus d, right?
Oh, okay, I see.
Right?
Yeah.
Okay, so let's see now. All right, so that's good. Okay. So what we do now, am I missing an X somewhere? No, this is right. Okay. All right. So what we do now is we compare coefficients, right? Here I have an X squared, right? Algebraically, this has to be true, right? So, so this is telling me, I hope everybody sees, this is telling me that 4a is equal to 1, right? Because I have this and I have this, right? The coefficients have to match. So 4a is equal to 1. There's a 1 in front of here, right? And here I got a 4a. So 4a is equal to 1. This is telling me that, let's see, that 4b is equal to 0, right? There is no x here, right? There's no x here, right? 4b is equal to 0, right? Because on this side of the equation, there's no x, right? And here I got a 4b, so my b has to be equal to 0. Okay. And then this is also telling me that the 2a minus 4c has to be equal to 0, right? Because here I got a 2a, right? I don't have any coefficient in front of the x. Here I got a 2a, here I got a 4c. And on this side, there's 0, right? So that's what we're doing. We're matching up the powers of x, right? The powers of x on this side and the powers of x on this side. Here, 4a, right? Here I got 4bx. Well, there's no power of x. There's no, so that's 0. Here I got 2a, 4b, but that's 0 here, right? So this is telling me now that, that a is equal to 1 over 4. A is equal to 1 over 4. And then this will be 2 times 1 over 4 minus 4c is equal to 0. Let's see. So what's c going to be? So let's see. So this will be, I can write this as 2 minus 16 C is equal to 0. I think it may be different in my notes.
I have a
Not
question.
different, but well, let me just finish this up, and then I'll be happy to answer any question. So then I got 16C is equal to 2. So C might, what is the plus sign here? Nobody stopped me. Was that your question? So then this is a minus. So C is equal to 1/8, minus 1/8. Yeah, there's a plus sign here. Okay. All right. So that's it. So the solution to this. So now I determined that A has to equal to 1/4, right? And B has to be equal to minus 1/8. Excuse me, C has to be equal to minus 1/8, and B has to be equal to 0. So my particular solution is A squared over 4, right? B 0, and then it's minus 1/8. Minus 1/8. So that's my particular solution. So the total solution, I guess let me put it down here. The total solution, the total solution is right. The total solution is going to be the complementary solution plus the particular solution. And you could check if you take the derivative of this and put it back in here, you better get that you better get x squared on both sides. So my total solution then is going to be C1 sine of 2x plus C2 cosine of 2x plus x squared over 4 minus 1/8. All right, a little sloppy there. But so that's my total solution. Any questions? So let me see. Good, we still got 15 minutes, 20 minutes actually. What I want to do now is let me let's see. I'm sharing my screen. Does everybody see the screen?
Yeah.
Yes.
Why is it taking so long to come up? Okay, so now we're solving the non-homogeneous differential equations. And I guess here's the problem we just solved, right? Here's the problem in my notes that we just solved, where we found the complementary solution and then we assumed the particular solution. Okay, and we'll learn maybe more about this tomorrow, but the particular solution must be linearly independent from the homogeneous solution. So, you know, so we got our constants, right? So this is what I just did. Okay. Okay, now here's some different examples. Okay. So if you had, in other words, if this function f of x was x squared plus 7, right? You're going to assume whichever the highest power of x. So in other words, when you got a polynomial like here, you know, we just got a first order. So you can assume that ax plus b. This table comes right out of your book, by the way. I took this table right out of your book. If you have any constant, in other words, if this is just equal to 4, right? Suppose this is equal to 4. You're going to assume a. You don't have to call it a. You can call it whatever you want. But you're just going to assume a. And then you're going to put that in the differential equation, right? So if you have something that's to the first power, you're going to assume, you know, to the first power plus a constant, right? If you have something to the second power, right, you can assume a second power plus a constant. The second power plus the first power plus a constant. So here, you see here, it's x cubed. So if my function of x, if I had a function that was x cubed minus x squared plus 1 on this side of the equation, the particular solution I'm going to assume is a time, you know, what I have written right here. If you have a sine or cosine, you're going to assume both sine and cosine, right? Because once again, what's the derivative of sine? It's cosine. What's the derivative of cosine? Well, it's minus the sine. But you don't have to worry about the constant. So, okay, so once again, for sine, you're going to assume cosine and sine. If you have an exponential, you're going to just assume an exponential times a constant. Now here, if I have like an exponential times a polynomial, right? I'm just going to assume the highest order polynomial, all right? So in other words, the highest order here is x squared, right? So I'm going to assume a solution that's ax squared plus bx plus c, all right? And then times the exponential. If I have something like an exponential times sines and cosines, all right, I'm going to assume a solution that has the exponential times sine and the exponential times cosine. All right. So, okay. So I guess you could see these here. This is about as complicated as it gets. Okay. We'll do some more practice. Let's see. Well, I guess maybe I'll go. Well, let me just talk about this now, being it's here. Suppose that like this differential equation here, right? This differential equation here, y double prime plus 16y. Hope everybody can see that the complementary solution is actually cosine of x squared plus sine of x squared, right? Actually, just when you have a differential equation of this form, just take the square root of this number, and that's always going to be your sine and cosine. Once again, it's got to be y double prime times y. Now, what I want you to notice here is that in this case, I can't assume, and we'll talk more about this one, I can't assume a particular solution of this form because I need, my particular solution has to be linear independent, okay? You see, my complementary solution is cosine of 4x and sine of 4x. I can't assume a particular solution of cosine of 4x and sine of 4x because that would make it linear dependent. I need a linear independent solution. So we do our old friend when we multiply by x. So in other words, for this differential equation here, right, I have to assume a solution. I have to assume a particular solution of ax cosine of 4x plus bx sine of 4x, right? So the rule is that if any particular solution contains terms that duplicate the complementary solution, then we multiply the particular solution by n to the n, x to the n, where n is the smallest possible positive integer that eliminates the duplication, okay? So for example, here we had this differential equation, right? This is the, turns out this is the complementary solution. So I can't assume a particular solution of the form e to the 5x, right? You cannot assume that. So I can assume a solution. So I can't assume this, but so instead I assume a solution where I multiply it by x, and that makes it linear independent. Okay. Let's see. All right. Let me just, I don't know if we, I guess we can go finish this video. Okay, so we want to solve this this differential equation given these initial conditions. Okay, so I have a video where we solve the yeah, this is okay, I guess this is going to run around 11 minutes. All right, if we don't, you can. So let's see. So the first thing I'm going to do is find the solution to
complementary solution, right? So all right, now I can find the characteristic equation or the auxiliary equation.
Yeah, by the way, some books call it the auxiliary equation, some books call it the characteristic equation.
And we don't need to use a quadratic equation for this. We can factor this. So let's see, so m is equal to 2, and m is equal to 3. All right, so my complementary solution is C1 e to the 2x plus C2 e to the 3x, right? That's my complementary solution. So we have to find the complementary solution first, right? Now I want to find a particular solution. And notice that that here I got an e3 to the x, and here I got an e3 to the x. So my particular solution has to be linear independent from these, right? So it means that I have to assume a particular solution that goes as a x e to 3x.
Okay, now just let me make sure that, suppose this was 4x, right? Suppose that the complementary solution that this was a 4x. Well, if this is a 4x, then I can assume 3x, right? But because this is a 3x, I got to have a particular solution has to be linear independent than these, okay? And so the way I make a particular solution that's linear independent is that I multiply it by x.
Right? So that's what I have to assume is my particular solution. Okay, so now let's take the derivative, the first and second derivative, and stick it here, and then compare the coefficients on both sides to find what a is. All right, so let's see. So let's take the first derivative. So they got to use the product rule here. So this would be I left out the a. Right, that's the first derivative. The second derivative. Let's see, this will be. Use the product rule here again. Let's see, so it's right. Okay, so let me put everything up. Let me put it up here now. All right, let me do this. I got more room. So let's see. So now I'm gonna put this right. Well, let me just. I'm gonna do this now, right? All right. I'm gonna put my particular solution. You know, the second derivative, the first derivative, and the function, and stick it here. So let's see. So what am I going to get now? I'm going to get, let's see, I'm going to get 3a e to the 3x plus 3a e to the 3x plus 9x a e to the 3x. Now here I got a minus 5, and then that's going to be times a e to the 3x, okay, plus 3x a e to the 3x, and then I have plus a x e to the 3x, and that's all equal to e to the 3x, all right? All right, so hopefully a bunch of things are going to cancel out here.
Forgot to multiply by 6, but I think I catch it.
Let's see here. I got it. Let's see. There's got a minus 5 here.
I watched this video. I know I caught it.
Let's see what we got here. Well, here I got a 6. Okay, let me
See, You can learn, I know it's not right. So I forgot the 6 here, but watch, I always find my errors.
A bunch of terms here. Here I got a 6a e to 3x. And on this side here, we have a minus 5a e to 3x, right? So that takes care of this, and this. Now here we got a 9xa e to 3x, and then we got a 15 here. Okay. Oh, and this is times 6. That's what the problem. This is times 6. All right. So they cancel out, right? I got the 9xa e to 3x. This is 15, right? And here I got a plus 6a. Okay. So these cancel out. And I'm left with a. Okay. So what do I have here now? So finally I have I got a e to 3x is equal to e to 3x, right? So a is equal to 1. A is equal to 1. So my particular solution is x e to 3x, all right? And my complementary solution is equal to c1 e to 2x plus c2 e to 3x. So my total solution is c1 e to 2x plus c2 e to 3x plus x e to 3x. Okay, so that's my total solution. Now we want to find the, we want to solve it for the initial conditions, right? We want to solve it for these initial conditions. So let me do that on a separate sheet of paper. So let me copy this down again. Let's see. So we got so when you apply the initial conditions, you have to be looking at the total solution, right? So this is our solution. And this is my initial conditions. Okay. All right. So all right. So let's see. So first of all, we're told that when y is equal to 0, it's equal to 0, right? When x is equal to 0, y is equal to 0. So it's going to be 0 using the first one is going to be c1, and then this is just going to be 1, right? Plus c2, and then this is to 0, right? And I put 0 in here. So I get one equation where I get 0 is equal to c1 plus c2. Now I got to take the derivative. I'm going to get 2c1 x to, it's not x, it's e, 2c1 2c1 e to the 2x plus 3c2 e to 3x. Now here I got to use the product rule. So it's going to be e to the 3x plus 3 e to the 3x.
Got the x.
All right. And now this is going to be equal to 2. So let's see. So I make this 2. And this is going to be 2c1 plus 3c2 plus 1. And here I left out an x here. All right, this is going to be 0, right? Now I use the product rule here. X is just 1, and then this brings down the 3. So I get 3x times e to the 3x. Okay. So, all right. So let's see. So I can write this as 1 is equal to 2c1 plus 3c2. Okay, let me write this like this. Put the other equation down here. Okay, let me multiply this equation by a minus 2. There's different ways of doing this. Let me copy this down first. So I'll make this 0. Then I'm gonna make this minus 2C1 plus minus 2C2. I want this to be minus, and then add these, and I get 1 is equal to C2. So C2 is equal to 1. Yeah, so C2 is equal to 1, and C1 is equal to minus 1. Okay, so my final answer that solves the differential equation in the initial condition is that y, but the total is equal to, let's see, it's going to be equal to minus, right? The C1 is my minus e to the 2x plus e to the 3x plus x e to the 3x. So that's it. That's it. That's our answer.
Okay, so this is actually got further than I expected today. That's good. And for the if I call this C2 and I call this C1, right? The only difference is that I would have gotten C2 to be 1. Excuse me. I would have gotten C2 to be minus 1 and C1 to be 1, right? If I call these differently. So it doesn't matter which one you call C1 and C2, to answer someone else's question. What actually turns out is that when you apply the initial conditions, you'll always get the same answer. All right, so that's it for today. The WebAssign problems that are where you have to solve the homogeneous differential equations, they're pretty straightforward. There isn't a lot of work in doing those, as you can see. But the ones where you have to do the non-homogeneous differential equations, you'll see there's a lot more algebra. Okay. All right. So if anybody has, I'll stay on. I think the plan is for me to. Someone had some questions. Someone had a question on their exam, and so I'll go over that. So that's it for today.
Thank you.
Have a good day.
Thank you,
Bye.
Professor. Have a great day.
Hey.
Professor, I
Yes.
have some troubles with 3 WebAssign problems.
Okay. I need to talk to somebody else first.
All right, then I'll wait.
If you could log off and then log back on,
In about how many minutes?
say 5
Okay.
minutes or so.
Also, you could have just put that person into a breakout room.
Okay. What are the WebAssign problems you're having problems with?
It was WebAssign 3.1 number 7
Or
and
3.1?
15, and then WebAssign 3.2 number 4.
Okay. Okay. All right. All right. Maybe maybe we could set up.
Or
I
maybe I
guess-
can come at 12:45 or 12:40.
Let's see. How about 1 o'clock? What
All
time?
right. All right.
Yeah. You use the same link. Okay. 1 o'clock.
All right. Thank you.
Okay. All right.
Professor?
Yes.
I'm on the meeting twice because I was recording from my computer, but then I was an emergency that I had to step out, but I'm still here. So my
Okay.
computer is at home recording. So if you end the meeting, it's gonna some way. If you don't end the meeting, it's just gonna keep running. So you can
Okay.
just end the meeting for me, okay?
Okay. No problem. Thank you.
Thank you. Have a great day.
Okay. Is anybody's if you're you said 1 o'clock, right? All right, I assume these people are probably not on.
Professor, I'm here to talk about the
Yeah.
exam.
You know, so sometimes they record and leave.
Yeah.
Okay, you know, I did take a look at your exam and I did notice something where I can give you more credit.
Okay.
Let me bring it up. Let's bring up your exam and let's see. Okay, just give me a second here. Okay, let's see. I'm getting there.
No rush.
Okay. Okay, so you see your exam coming up?
I do.
Okay, well, let me first, I'm actually glad you came to me, okay? It's always, what happened here? I'm not seeing the screen. What the heck happened?
It's showing on the Zoom.
It's showing to you, it's not showing to me. I don't know what's going on.
That's weird.
Okay, now it is, okay. All right, so, first of all, let's go to problem number 6.
Okay.
The, yeah, problem number 6. Okay. Yeah, problem number 6. It wasn't clear to me. I thought that now I see what you were saying. Problem number 6, I thought you would, I saw this red line. I didn't understand what this red line was. And
I
and
think
then,
it was.
yeah. So anyway, it seems to me, I want to make sure that you understand it, but you should have drawn the curve like this, okay? In other words,
All the way out.
right, and you should draw it up like that. That was the idea. But I tell you, I think you understand it, right?
Right.
All right, so I took off on that problem there. I took off 4 points. So I'll give you the 4 points on that. Okay. I won't,
Okay.
because but try to be a little bit clearer. You know, I was expecting to see the lines go all the way. But I'm
Right.
assuming now that you understand. So we'll get
Yeah, I
rid of-
think that was sort of the same thing. I think you mentioned last class that you gave credit for the first question, even if they didn't draw it all the way out.
I think the first question I gave you full credit. All right.
You did.
Now here you said is nonlinear. I couldn't find the answer, but now I see
Right.
that you have the answer way deep down here at the bottom.
Right.
All right, so I could we could mark that correct.
Okay.
All right, but to be honest, I think that's all I found. That
So
Alright,
can you
so-
just clarify the trig?
yeah,
then?
I'll be happy to. Be happy to.
Okay.
So all right. So first, yeah. So let's see. So right now that gives you 5 more points at least. So that gives you a 61. Just let me, in case we go more, so I don't forget. We'll do it.
Okay.
So this is gonna be a 61. So let's. And so that's going to help quite a bit. Let's figure out what. So let's see, 61 divided by 80. Okay, so this, all right, so this is gonna, okay, so I'm gonna make this a 77. I normally I'll round up. All right. So, all right, so let's see now if there's, I don't, to be honest now, I don't think there's anything else, but let's, we could definitely go through it. So I gave you full credit on this. I
Yeah.
didn't take off any points on that. Full credit on that. Okay, I gave you full credit on this. Okay. Got full credit. Okay, now here, the answer is no, there is not, well, there's two things here. For this problem here, and I took off 5 points for everybody who didn't use trig substitution. Okay. So take a look at my solutions. I can bring up my solutions too. If you look at my solutions, you'll see what I mean by trig substitution. All right. And then the other thing too is the answer here is no. There is not a unique solution. And the test you have to apply, once again, you need to apply the test that I show. You know, I show the solutions. You need to apply that test.
Okay.
Okay. The other thing here is you're taking the inverse wrong. All right. Let me stop sharing for a second. Okay. When you have x, like if you have the inverse sign of x was equal to, what was it? What did you have again? Let's see.
I think it was x squared over x plus c.
Okay. Okay, it was actually the sine of y was equal to 1/2 x squared plus c. Okay. Well, first of all, you don't have the right answer. Okay. And when you take the inverse, this is going to be y is equal to the sine of 1/2 x squared plus c. In other words, the c has to be in the argument. The c, it's not, this is wrong. You have the c out here, right?
You
And
can't just make it c2.
No.
Like, okay.
No. When you take the inverse, you have to, and the correct solution, take a look at the correct solution and make sure you know how to do it. I think the correct solution, hold on one second. Okay, yeah. So the correct solution to this problem is y is equal to the sine of 1/2 x squared plus c. So you had your, you had, for some reason, you have y is equal to the sine of x squared plus 2 plus 1, right? That these are definitely not the same. Okay.
Okay.
Now, and then you didn't do the trig substitution. Now, in the other problem, the correct answer on the other problem is x is equal to the tangent of 7t minus 6 pi over 4. See, what you have, we're looking at yours now, right?
Right.
Okay. All right, let me go, let's see. Compare your answers with mine. Okay.
So I think where I tripped up is I just didn't put the c in the trig function.
Right, right.
Okay.
See, and you didn't apply the initial conditions for number, the problem for number 4, problem number 4,
Mm-hmm.
let me, see, in problem number 4, this is the correct answer for problem number 4, or you can write it like this. Okay, you can write it like
Okay.
that, right? So that's problem number 4. So I think I was fair on problem number 4.
All right.
Then this one here, you can't separate this. You know, it really just turned out to be a coincidence. This is, you can't go from here to here. It's impossible. The algebra doesn't work out. In other words, you had to do some algebra to go from here to here. It doesn't work out. This equation you had to solve, you couldn't separate this equation. You had to solve it by the method of an integration factor. Okay. So you didn't use the method of an integration factor. And then there is a transit term. And basically this is a transit term. All right. If, you know, for your solution, this is the transit term. So you should have said yes for a transit term, not none. But take a look at my solution and make sure you understand it. You have to, on the final, you will have a problem where you have to integrate using an integration factor. Okay.
Okay.
So, yeah, so let's see. I'm going to change it right now to a 77. And, you know, you still have you know, you're not far from a B. It's not a bad grade. So, you know, you could still get an A for the course. There's no reason why you still can't get an A for the course based on what's left.
All right. I just wanted to clear some things up. That trig
How did you
made
do
a
in
lot more
calculus
sense.
1?
I'll-
How'd you do calculus 1 and 2?
Hmm?
How'd you do in calculus 1 and 2?
I got A's in both.
Okay. Okay. All right. Let's get an A in here. There's no problem getting an A. But
Okay.
make sure you understand how to do the integration factor, okay? You
All
can watch
right.
the video, look at what I did, and so on. Okay.
Okay.
And I apologize for not, well, basically, I didn't see it up, you know, the last problem, I didn't see that where you stated it.
No, you're totally fine. I guess it could be weird to see like the first question at the bottom of the page instead of at the top.
All right. So if you now go to my grade, you'll see that that you have a 77.
All right. Thank you so much.
Okay, you're welcome.
You have a good day.
You too.
All right. Bye.